Welcome to the tutorial of this Lumerical. So basically here I will show you the basic simulations using Lumerical and the functionality of the Lumerical, what component to use and when to use, what is the utilizations of boundary conditions and all those things that I will discuss over here. Always you should remember that first thing first. It means obviously that when you are going to simulate a particular object, so you should put that object first in the simulation region. But it doesn't mean that always the object you have to put first. You may put the simulation region and any other thing. I'll discuss one by one. This black windows. They are the background material or background medium over which you are going to import that structure, or you're going to design that structure. Okay, so the background medium is generally the refractive index of the background medium is by default it is set to 1, means it is the free space, okay, or the air medium, and you can change the background medium also. So first of all, before discussing this Lumerical simulation software, I should mention or I should explain how this software works and what is the background feature. Although I'm not discussing in a greater detail, but a very simplest manner I should explain, so that during the simulation you can have an idea, so that you can debug your programming, or you can debug your simulation. The name of this software is FDTD. Although in the Lumerical package there are lots of softwares, what I will explain over here and where you will do your job, that is on FDTD. Now FDTD stands for Finite Difference Time Domain, which means already you have studied the numerical methods in mathematics. So basically this is the almost similar idea, but in a complex manner. Lumerical FDTD deals with the Maxwell equations, solving Maxwell equations. Okay. Now Maxwell equation, we know it deals with the both space derivative and time derivative. For example, I'm just taking only one equation, that is the Faraday's law, that is curl of E is equals to minus del B del T. If we take this curl, so what do we get? We get generally as x cap, y cap, z cap, del x, del y, del z, ex, ey, and ez, which is equals to minus del b del t. So there are we are getting three components. So this is the x component, this is the y component, and this is the z component on the left hand side. In a similar manner, the right hand side we can write, so every component on the right hand side must be matched with the every component on the left hand side. If I consider only one component, say for example the x component I'm considering, now there exists this differentiation. Okay, this is the space differentiation and this is the time differentiation. Now these things are implemented in the software, this kind of differentiation. Now and as we know, when Faraday's law and modified Ampere's law they are combined, the traveling waveform or we can generate, or we can have the traveling wave equations. Okay, and that the solution of that equation basically explains how the electromagnetic wave travels. Okay, similarly, if we simulate these equations for all these three directions, I mean if we implement these three equations, all these three directions, along with the modified Ampere's law, and we combine them in a similar manner that we do mathematically or we derive for our theoretical classes, then we can visualize the propagating wave, the same thing that you are going to visualize using the software. Now how these things, I mean how this derivative works. So here there's a complex derivative. I'm not going to discuss this complex derivative, rather I will just simply discuss, suppose there is a path. Okay, suppose this is x equals to a and this is x equals to b. Now in between this, there are you have to integrate, or sorry, you have to differentiate any function. Suppose this is, suppose fx is given a function that you have to integrate over this path. Okay, sorry, you have to differentiate from this limit x equals to a to up to x equals to b. Now the what is the differentiation f dash x? What is the definition of the differentiation? We know df dx delta x tends to 0 f of x plus delta x minus fx divided by delta x, or limit delta x tends to 0 f of x minus f of x minus delta x divided by delta x. So this is the basic definition of the differentiation. Now what is delta x? Delta x means how small you can choose a segment. How small you can choose a segment, the more accurate your calculation will be. Because in this case I have drawn a straight line for the fx, but practically this fx cannot be a straight line like that. So df dx is quite obvious. If this is x, this is fx, quite obvious is df dx represents the slope. Now if I consider this delta x so large that it includes, this is suppose x1 and this is x2, so x2 minus x1 is equals to delta x. Okay, now if I take this corresponding value of fx or delta f, okay, so that will never give you the accurate value of delta f over delta x, which is the slope or the rate of change of f with respect to the x. Because I have chosen these x, the difference between in this x, so large that includes a very arbitrary variations. So that's why, to avoid that thing, we generally choose delta x tends to 0, so that if I choose delta x tends to 0 somewhere over here, so delta x will be so small so that this segment over which I'm considering, this segment that I'm considering, that thing will be linear. So it will be very much helpful. So for this linear assumption, we can calculate the rate of change of this function with respect to the change in delta x. Okay, for this linear assumption. So from the same argument, I can say that the smaller the segment I will consider, the more accurate my result will be. Okay, so that's why delta x tends to 0. Okay, I mean the Maxwell differentiation equations goes on the basis of this principle. Okay, but the delta x we have to choose as small as possible. But if we choose very small, we can choose arbitrarily. Delta x can be 0.000001 or even less. But if we choose arbitrarily, the calculation time will increase. Okay, because if we differentiation from this point to this point will take much smaller time compared to if we take 100 divisions or 1000 divisions over this line. Okay, so that's why we have to choose a proper value for this delta x. Generally, for this type of simulation, we mention the wavelength. Okay, and wavelength is the key factor. Wavelength is the key factor. So this is the wavelength. So when an electromagnetic wave propagates over a complex structure, so that electronic wave should have some wavelength. So in this case, this is the wavelength, and I'm considering this wavelength is lambda. Okay, now you have to choose these grid points. They are called grid points. Okay, I mean when we're doing the simulations, we'll call them grid points. So we have to make these grid points such a manner that the minimum criteria is at least 10 grid points should be per wavelength. So from there to there should be 10 grid points. Okay, the smaller the grid point you will consider, the more accurate will be your results. Okay, But here during this simulation we will see that even 2000 grid points also I will consider for two-dimensional simulation. Okay, so I hope you have understood the mechanism. Generally, whatever you will consider, or what the smallest step you have to consider, the smallest grid point you have to consider, that should be with respect to your wavelength. Okay, now let's consider this particular simulation environment. Now here I'm going to bring this simulation. Now what is this simulation? This simulation is basically the domain within which your calculation should be confined, or only that particular domain you have to consider, because this medium is infinitely extended. Okay, so here I'm going to place, this is the, there exist two things. Mesh is basically the additional grid lines that I mentioned. There are default mesh lines that or the default grid lines available within this region. Okay, I will show you. But if you need more accurate result, obviously that will involve much more computational resources. But if you need more accurate results, then you can bring this mesh and the additional mesh or additional grid points within your simulation region. Okay, so that's the simulation region first I'm going to consider. Now this is the simulation region. So within this, these are the boundaries, the four boundaries you have. Now this one is the XY view, this one is the XZ view, this one is the YZ view, and this one is the perspective view. Okay, basically this simulation is three-dimensional in nature. Okay, well, now what is this FDTD? FDTD is the mathematical or numerical boundary over which you can simulate. So if I go to edit object, right clicking over edit object, so I will get these dimensions. So this is the three-dimensional simulation. By default it is selected as three-dimensional simulation, but most of the cases we generally do two-dimensional simulation, and for our purpose, for the surface plasmon resonance, most of the cases we will go for the two-dimensional simulation. Okay, so I'll just click it over here. Simulation time 1000. We should not change this one. These are the advanced settings. Okay, if you will be confident enough to change this, and you know how the simulation time works, then you can probably change this. Otherwise, don't touch it. Geometry. This is the position of the this FDTD or the simulation region. This is the spanning, minimum x, minimum y, and all these things. These are you can understand. This coordinate system are self-explanatory. Meshing. This is the meshing or the grid points that I just have explained. Look, minimum mesh step is 0.00025. Okay, so this is the minimum meshing steps. This is the time stepping. There are relation between this mesh step is related to the space within the space domain, and this is the time stepping, minimum time stepping required. There are certain relations. I'm not going to discuss about that. Okay, the stability factor also related to these relations. Now mesh accuracy. If you increase this one, so obviously the grid points will be much denser, and your numerical calculation will take much more time. Okay, and this is the mesh type. We can go for auto non-uniform meshing, custom non-uniform meshing, or uniform meshing. But instead of uniform meshing, we generally prefer to non-uniform meshing. Because why non-uniform meshing? For example, I have a complex structure. Okay, for a complex structure there are lots of interfaces. Suppose, okay, for example, I have a complex structure. Okay, say this one and this one. This is a complex structure penetrating one into other. So there are interfaces. So I'm just marking these interfaces. This is the interface. Okay, so there's a complex structure, as you can see. Before this one, within this complex structure, only this part is a significant one. This part is significant one. Why? Because the penetration exists over here. Other than this region, all other regions are uniform in nature. Okay, this region is uniform. This region is also uniform. Okay, so if we do uniform meshing, and if we need to if you need a very accurate calculation, So in order to get a denser meshing over there, we by default we also have to increase the meshing over there, because we are choosing uniform meshing. The mesh step or the uh, distance between 2 points will be uniformly distributed, but that will increase your simulation time, while you do not need much more accurate calculation within this region. Rather, you need a detailed calculation or accurate calculation only for this region. Okay, so that's why non-uniform meshing helps us. It meshes coarsely within the unimportant region and densely within the uniform region. So we should prefer for the non-uniform meshing. Okay. Next, coming the boundary condition. Now, what are the boundaries? These are the boundaries. Okay, what boundary I should choose? Now look at here. Initially, I have chosen 2D. Now, if I choose 3D, this three-dimensional boundary is appearing. Means minimum x boundary condition. If you observe, this is the xy view. So this is the minimum x. This is the maximum x. This is a minimum y. This is the maximum y. And for z, you have to observe this xz or yz view. So this one is the x direction, this one is the z direction. So this will be the top one will be the maximum z boundary, and this one will be the minimum z boundary. What are the boundary conditions? This is the first one. First one is the PML, perfectly matched layers. This PML is basically the absorbing boundary conditions, and there are lots of boundary conditions. I will discuss one after another later on, but not right now. Okay. So absorbing boundary condition means when I will do this simulation, you will see that the after initiating the simulation, the wave, when will propagate along a particular forward direction, after reaching the boundary, the wave will be absorbed, implying that until and unless the wave is facing or being introduced to some diffracting medium or reflecting medium, the wave is passing on to the infinity. But numerically, how we can achieve that thing? So numerically, we put the boundary condition, which is called PML, a perfectly matched layer, which is the absorbing boundary conditions. The waves are the waveform gets absorbed over there, implying that the wave is not returning back or not reflecting from the boundary. Okay. Well, so I'm applying. Now I'm going to the source. So here I am choosing the plane wave source. Look, as I've chosen these plane wave sources, for this source, the direction is by default along the z direction. So I can choose this edit object, and this injection axis. Injection axis is I will choose along the x direction, means along this direction. Now this angle theta, it represents along which directions the wave is propagating. In this case, as theta is equals to 0, you can see the wave is propagating. This is this pink color arrow represents the direction of the wave, and this blue color arrow represents the direction of the electric field or the direction of the polarization. Okay. Now, if we put theta is equals to, say, for example, arbitrarily 45 degree, the direction of this injection direction will be changed, as you can see over there. Okay, if you put minus 45 degree, that will be in opposite direction, making 45 degree angle with the x-axis. Okay. Now this polarization angle. Okay, polarization angle means in this case, since it is 0, the electric field is lying on the xy plane. Now if you make polarization angle 90 degree, so this electric field will be vertically towards you, as you can see. Okay, and it will be very much clear if you observe the xz plane. Right now the electric field is along the z direction instead of the xy direction, but if you put it is 0, then it will be along the xy plane, on the xy plane. Now phi angle, it represents the orientation of the electric field. As you can see, depending upon the phi, you can initiate the circularly polarized wave or elliptically polarized wave if you rotate this angle phi. This angle is basically the angle between the uh, electric field component that exists perpendicular to the direction of the propagation. Okay? Now, based on this angle, you obviously can give a linear polarization, circular polarization, as well as elliptical polarization, okay, which are not required for our purpose right now. Geometry, you can choose geometry directly from over there, or you can drag it to your appropriate positions. Say for example, over there. Now the wavelength. Wavelength, you can choose either frequency or wavelength. In general, we'll choose wavelength. This is the format. Either you can choose the center and span format, or you can choose mean and max format. So in this case, I'm choosing 0.4 and 0.4 for a single wavelength. Okay. Well, now as I have chosen this 0.4, now coming to the mesh setting. As I told that the number of grid points should be integer within a wavelength. Okay. Now, as this mesh step is this one, single mesh step. Okay, and your wavelength is 0.4. Mesh step is 0.00025, and the this is delta x. Say for example, in this case, I'm just relating my explanation in my earlier slides, and wavelength is 0.4 micrometer. So if I divide this lambda by this delta x, what I will get? 0.4 by 0.00025 micrometer. So within one wavelength, how many grid point you will have, that you can calculate, and that grid point must be integer. So what I will get? 1600. This is the number of grid points that I will have within the one wavelength. Okay. Now today first I will explain the propagating wave, how you can see the propagating wave. So for that, there are lots of monitors. I will explain one after another the functionality of the monitor in my successive videos. So first of all, I will choose the movie monitor. Okay, so that movie monitor will give you a visuals how the electromagnetic wave is propagating along the direction. Now first I should go for save. Now running. This is yes, this one is taking very longer time because I have chosen this is as 3D. So I choose it 2D because this is a very simple simulation. We do not need any 3D calculations. Just reducing the time and to explain how the electromagnetic wave propagates. Directly you can play it over there, and sometime it doesn't work. Then you have to go for, well, as you can see, but hold on. The wave is propagating along this direction, and eventually you will see that nothing is reflecting back because there exists the absorbing boundary condition, which is called PML. As you will see, that wave is gone and fully absorbed. But another thing you should observe. Just hold on. Look, the wave is propagating along this direction. My intention is that the wave must be absorbed along the forward direction. But what about this? Along these directions, they are also being absorbed because the absorbing boundary exists all around. So along the transverse direction, they are also being absorbed, which I don't want. Okay. So what I should do over here, I'm just changing the boundary condition for the FDTD along the y direction, because as it is propagating along this direction, along the x direction, they will be absorbed. Along the y direction, they must not be absorbed. So along the as you can see, y minimum boundary condition, the z boundary condition is absent because the 2D simulation I am doing, so automatically z boundary condition is gone. So y minimum is periodic, I'm choosing, so automatically y maximum also will be periodic. Or you can choose the block and periodic. They are similar in nature, but when you are injecting your wave directly perpendicular to the device or to the object, as you can see over there, then you should choose or you can free to choose the periodic boundary condition. But if you are injecting this your wave by making an angle, that means the oblique incidence, in case of oblique incidence, you should choose the block boundary condition along these transverse directions, in order to mention, or in order to ensure that nothing is absorbing along the transverse directions. Okay, so now once again I'm running. In this case, as you can see, you should remember that they are getting absorbed along the transverse direction, and I hope you will see right now that look, they are not getting absorbed. Look, along this direction they are not getting absorbed. Only the absorption is taking place only the forward direction. Okay, so for now I hope it will help you, and in my next video I will explain the structure also. Okay, and the structure and the monitors, one after another I will explain.